Hello and welcome to yet another video of Cornerstones of Math. In this video, I explain the entrance exam of year 2024 from Chennai Mathematical Institute, a distinguished higher education and research institute in India specializing in physics, math, and computer science. The Bachelor of Science or undergraduate entrance exam is divided into two parts. Part A consists of moderately difficult problems. Part B consists of 6 very difficult problems and are only graded if students meet certain criteria in Part A. One of my viewers suggested that I should explain these 6 problems in Part B, and upon examination, I found that the problems are both extremely difficult yet also quite interesting. So let's dive into these 6 problems. Problem B1. There are 2 problems, A and B, and let's take a look at problem A first. Draw a qualitatively accurate sketch of the unique bounded region R in the first quadrant that has maximum possible finite area with boundary described as follows. R is bounded below by the graph of y equals x squared minus x cubed, bounded above by the graph of an equation of the form y equals kx, where k is some constant. Also, R is entirely enclosed by the 2 given graphs, i.e. the boundary of the region R must be a subset of the union of the given 2 graphs, so R does not have any points on its boundary that are not on these 2 graphs. Clearly mark the relevant points on the boundary where the 2 given graphs meet and write the coordinates of every such point. Alright, first the lower boundary, the graph of y equals x squared minus x cubed. You can write the equation as x squared times 1 minus x. So the graph passes through points 0, 0 and 1, 0, and because x is squared, the graph is tangent to x-axis at 0, 0. That is, at x equals 0, the graph touches the x-axis but does not intersect. You can easily verify this mathematically by showing that the value of the derivative at x equals 0 is 0. Moreover, this is a cubic function with negative leading coefficient, hence the graph must have decrease, increase, then decrease again shape. Therefore, we have the following graph. The graph of y equals kx is a straight line passing through the origin, and together with the graph of a cubic function, they form a boundary of region R. Changing the value of k changes the slope of the line. So when does this area become maximum? Well, this area is maximized when the line is tangent to the graph of the cubic function. That is, 2 graphs meet at a single point on the first quadrant. In order to find the value of k in this case, let t be the x-coordinate of the point of tangency. When 2 graphs are tangent like this, we can think of 2 conditions. First, 2 functions must have the same y value at x equals t, hence we have kt is equal to t squared minus t cubed, and because t is non-zero, we can write k equals t minus t squared. Second, 2 graphs must have the same slope at x equals t. Using the derivatives, which is 2x minus 3x squared for the cubic function, we have the condition k, the slope of the line, is equal to 2t minus 3t squared. We can easily solve this system of equations by equating the right-hand sides of 2 equations. So this rearranges to 2t squared minus t equals 0, and because t is non-zero, we obtain the value t equals 1/2, which gives the k value k equals 1/4. Therefore, at the maximum area case, the slope of this line is 1/4, and the coordinates of the point of tangency are 1/2, 1/8. Let's move on to problem B. Consider the solid obtained by rotating the above region R around y-axis. Show how to find the volume of this solid by doing the following. And the problem says you don't need to find the exact value of the volume, and it is sufficient if you just present the mathematical expression to calculate the volume. but it is actually possible to find the exact value of the volume, and I will present that value as well in this video. The problem can be solved in two ways because there are two methods to calculate the volume of the solid of revolution. We are only thinking about revolving around the y-axis here. The first method is the disk method or washer method. Suppose that we want to find the volume of the solid obtained by revolving the region between the graph that can be expressed as x equals f of y and y-axis around y-axis. In a nutshell, calculating the volume is first calculating the infinitesimal volume at a specific coordinate y and adding them up, which results in an integral. In this case, the volume element is a disk with a circular cross-section and an infinitesimal thickness dy. The cross-sectional area is pi times x squared, hence the volume of the disk dv can be expressed as pi x squared times dy, so pi times f of y squared dy. Therefore, the volume of the solid of revolution can be expressed as pi times integral of x squared dy or pi times the integral of f of y squared dy. If we want to find the volume of the solid obtained by revolving the region between two graphs, x equals f of y and x equals g of y around y-axis, then the infinitesimal volume element now becomes a disk with a hole, also called a washer. It is easy to notice that the cross-sectional area now becomes pi times f of y squared minus g of y squared, and this times the thickness dy gives the volume dv. So the volume of the entire solid is pi times the integral f of y squared minus g of y squared dy. In our problem, the outer graph, the cubic function, must be f of y in the formula, and the inner graph, the line, must be g of y. But we have a problem. The given cubic function cannot be expressed in x equals f of y form. But we can still use this method though. Here the interval of integration is from 0 to 1 over 8. The second integral is for revolving the line around the y-axis. Hence it gives the volume of a cone. As for the first integral, we can change the variable into x using the given cubic function relation. Since y equals x squared minus x cubed, dy equals 2x minus 3x squared times dx. Therefore, we obtain the first integral becomes f of y squared, so x squared, then dy, which is 2x minus 3x squared dx. Notice that the interval of integration also changes, now from 0 to 1/2 the range of x. And as for the second term, we can simply use the formula to calculate the volume of a cone, which is 1/3 times pi times the radius of the base is 1/2, so 1/2 squared, and the height is 1 over 8. So if we carry out the integration and do the math, we obtain the volume pi over 480. But there's another method to calculate the volume, also known as the shell method. Here, the situation is a little bit different. We have a graph given as y equals f of x. And this time we have the region between this graph and the x-axis. We revolve this region around y-axis, and we want to find the volume of the resulting solid of revolution. If we revolve the rectangular region having infinitesimally small thickness dx located at coordinate x around the y-axis, we obtain a thin cylindrical shell. Here dx is infinitesimally small, so that the volume dv of the shell is just the area of this thin rectangle times the circumference of the circle. The area of the thin rectangle is y times dx, and the circumference of the circle is 2 pi x. So we have 2 pi xy dx or 2 pi x f of x dx. Therefore, the volume of the entire solid of revolution is given as 2 pi times the integral of xy dx. So 2 pi times integral of x fx dx. Just like the previous method, this formula can be extended to the situation of revolving the region wedged between two graphs, now having the same interval for x, with the upper graph being y equals f of x and the lower graph being y equals g of x. The only difference here is that the height of the cylindrical shell is changed to f of x minus g of x. So we have the formula 2 pi times integral x times f of x minus g of x dx. So let's apply this formula to our problem. This time, f of x must be the upper function, hence it is the linear function. And g of x must be the lower function, hence it is the cubic function. Therefore, the volume is given as 2 pi times integral from 0 to 1/2 x times the linear function 1 over 4x minus the cubic function x squared minus x cubed. So we simplify the integrand, and we do the integral, and this gives the volume pi over 480. Now the problem B2. Problem A, find the domain of the function g of x defined by the following formula. G of x equals integral of log base 10 of log base 10 of t squared minus 1000 t plus 10 to the power of 1000 dt from 10 to x. Calculate the quantities below. You may give an approximate answer where necessary, but clearly state which answers are exact and which are approximations. Problem B wants us to find the value of g of 1000. Problem C wants us to find x in the interval from 10 to 1000 where g of x has the maximum possible slope. Problem D wants us to find x in the same interval where g of x has the least possible slope. And problem E wants us to find the limit of ln x divided by gx as x approaches infinity if it exists. Also, the official solution mentions the bonus problem, which is to investigate the limit of x times ln x divided by gx, and I think this is a pretty interesting question, so I am going to deal with this in the video too. But first, let's start from problem A, finding the domain of the function. G of x is defined as an integral, hence we must find out when the integrand function can have a value and when it cannot. The integrand actually consists of two logarithmic functions, hence we must find the condition for t where both logarithms can have a value. In order for a logarithm to have a value, the argument of the logarithm must be positive, so we have t squared minus 1000t plus 10 to the power 1000 is positive from the inner logarithm, and log base 10 of t squared minus 1000t plus 10 to the power 1000 is positive from the outer logarithm. As for the second inequality, this means that t squared minus 1000t plus 10 to the power of 1000 is greater than 1. So t squared minus 1000t plus 10 to the power 1000 minus 1 is greater than 0. Here, if you examine the discriminants of both quadratic equations, you can easily notice that they are both negative, simply because this 10 to the power of 1000 is way too large compared to other terms. This means that both functions on the left-hand sides are indeed always positive, so that both inequalities are true for all real numbers t. Therefore, the integrand can be defined for all real numbers t and forms a continuous function. Therefore, g of x can be defined for all real numbers x. So now that we found the domain, let's move on to problem B, finding the value of g of 1000. Well, as for the starter, g of 1000 is the value of this definite integral. Now, if you attempt to integrate the given logarithmic function, you will soon find out it is impossible to integrate the given integrand function and express it using the standard functions we commonly use, meaning that it is impossible to find the exact value of this integral. Therefore, as stated in the problem, let us try to find the approximate value of this definite integral. The key for approximation is realizing that in our interval of integration, which is t is from 10 to 1000, the magnitude of t squared minus 1000t is way smaller than the constant term, which is 10 to the power of 1000. Therefore, we can just ignore this t squared minus 1000t part and assume that the innermost quadratic function is approximately equal to its constant term, 10 to the power of 1000. So g of 1000 is approximately equal to the integral of log base 10 of log base 10 of 10 to the power of 1000 from 10 to 1000. Here we have log base 10 of 10 to the power of this number at the exponent. So this part simply gives this value at the exponent. So the integrand is simply log base 10 of 1000. And log base 10 of 1000 is just 3. So we simply have the integral of 3, which gives us 2970 as the approximate value of g of 1000. Next, let's deal with problems C and D at the same time, because they essentially ask the same thing. We have to find x in the interval 10, 1000, where function g of x has either maximum possible slope or least possible slope. Since we are talking about the value of slope here, we must find x which makes the derivative g prime of x maximum or minimum. If you have learned the fundamental theorem of calculus, you may understand that the derivative is equal to log base 10 of log base 10 of x squared minus 1000x plus 10 to the power of 1000. Here, log base 10 of something is an increasing function, meaning that if the inside part increases, then the value of the logarithm also increases. Therefore, we only need to investigate when the quadratic function x squared minus 1000x plus 10 to the power of 1000 becomes maximum or minimum. This is a convex quadratic function that is symmetric with respect to x equals 500. Therefore, it is minimum at x equals 500, and between two endpoints 10 and 1000, 1000 is farther from 500, hence the maximum occurs at x equals 1000. Therefore, the slope is maximum at x equals 1000 and minimum at x equals 500. And the last one, problem E, limit of ln x divided by gx as x goes infinity, and the bonus problem that I mentioned, the limit of x ln x divided by g of x. Let's do the main problem first. First, notice that both numerator and denominator goes to infinity, so the given limit is in infinity over infinity indeterminate form. Therefore, we can think of applying the famous L'Hopital's rule and see what happens. By L'Hopital's rule, the limit of ln x divided by g of x is equal to the limit of the derivative of ln x, hence 1 over x divided by the derivative of g of x, which is equal to this. And here, notice that the numerator approaches 0, but the denominator goes to infinity. Therefore, the value of this limit is 0. And the bonus problem, which is a bit more interesting. We have to find the limit of x ln x divided by g of x, and let's use the L'Hopital strategy again. So by L'Hopital's rule, now we have the limit of the derivative of x ln x is ln x plus 1, so ln x plus 1 divided by g prime of x. Examining the derivatives, you can realize that this limit is still in infinity over infinity form. Therefore, we use L'Hopital's rule again, which leads to this expression involving the second order derivative g double prime of x. In order to obtain the second order derivative, we use this expression for the first order derivative, and the formula for the derivative of log base a of x, which is 1 over x ln a. This gives the following lengthy expression. First, we must differentiate the outermost log base 10, which gives 1 over its inner part, hence the inner logarithmic function, times 1 over ln 10. Then by the chain rule, we must differentiate the inner logarithmic function, which gives 1 over its inner part, x squared minus 1000x plus 10 to the power of 1000, times 1 over ln 10. Then by the chain rule, we must differentiate this quadratic function part, which gives 2x minus 1000. If we rearrange this, we obtain ln 10 squared times x squared minus 1000x plus 10 to the power of 1000 times log base 10 of x squared minus 1000x plus 10 to the power of 1000 in the numerator, and x times 2x minus 1000 in the denominator. Here, notice that the denominator is a quadratic function, and the numerator is a quadratic function multiplied by the logarithmic function, so the behavior is similar to x squared ln x. Therefore, the numerator increases faster than the denominator, hence the limit is infinity. Now there are other methods which involve less L'Hopital's rule, so that we don't have to obtain the second order derivative at all, but unfortunately such methods require some other advanced concepts which I think is far beyond the scope of this test. One more thing. Some of you might want to use graphing tools to plot the function g of x and visualize the limit behaviors we have discussed so far. Unfortunately, plotting the exact graph is practically impossible, simply because the constant term 10 to the power of 1000 is way too large, larger than the upper limit value for most of the computer programs, which is approximately 10 to the power of 308. However, if we modify the constant term in g of x to a low enough value so that it can be handled by the graphing calculator, say 10 to the power of 100, and call this modified function g1 of x, then we can visualize the graphical behavior of several functions involving g1 of x. As you can see, the graph of ln x divided by g1 of x decreases and approaches 0, but the graph of x ln x divided by g1 of x actually increases, albeit very slowly, when x is sufficiently large. Now let's move on to problem B3. Problem A, for non-negative numbers a, b, c and any positive real number r, prove the following inequality, which is a to the power of r times a minus b times a minus c plus b to the power of r times b minus a times b minus c plus c to the power of r times c minus a times c minus b is greater than or equal to 0, and state precisely when equality is achieved. The hint says we can assume that a is the greatest number and c is the least number, and we are going to use that. And we will deal with problems b and c later. So first, as suggested in the hint, we can indeed assume that a is greater than or equal to b and b is greater than or equal to c without loss of generality. This is because the expression on the left-hand side of the inequality is given in a perfectly cyclic or symmetric manner. That is, if we interchange any two variables, then we obtain the same inequality, and consequently, if we replace a, b, c with any other possible permutations of a, b, and c, we still obtain the same inequality. So, assuming this ordering without loss of generality, let us deal with first two terms. Here notice that a minus b is common, hence we can write a minus b times a to the power of r a minus c minus b to the power of r b minus c. Here, a minus b is greater than or equal to 0. As for the second factor, since we have the ordering a is greater than b and b is greater than c, we also have a to the power of r is greater than b to the power of r and both are non-negative, and a minus c is greater than or equal to b minus c and both are non-negative. This gives a to the power of r times a minus c is greater than or equal to b to the power of r times b minus c. So from these two, we know that the first two terms are non-negative. Since we have to obtain the equality condition for the entire inequality anyway, let us think about the equality condition for above inequality as well. From this expression, you'll notice that the equality holds when a equals b, or a to the power of r times a minus c equals b to the power of r times b minus c. Now, some of you might think that this eventually ends up with the condition a equals b equals c. Well, the equality does hold if a equals b equals c, but it is not the only possible condition. When a equals b equals c, both a minus c and b minus c are 0. But they don't necessarily have to be 0. You see, under the assumed ordering right here, another possibility is when c equals 0 and a equals b. So 0 here, and this times this is equal to this times this. So this is the equality condition for first two terms. And with this condition in mind, let us take a look at the remaining third term. This is quite easy, by the way. The third term, c to the power of r times c minus a times c minus b, is greater than or equal to 0 because under our assumed ordering, c to the power of r is greater than or equal to 0, and c minus a and c minus b are both less than or equal to 0. Hence, the product of these three are non-negative. The equality condition for the third term is when c equals 0, or c equals a, or c equals b. Therefore, we know that the given inequality is true. The equality condition is that conditions 1 and 2 must be satisfied simultaneously. And if you ponder for a moment, you'll notice that the common condition between these two is just condition 1. That is, if condition 1 is satisfied, then condition 2 is automatically satisfied, or you can also say like condition 1 implies condition 2, or condition 1 is sufficient for condition 2, etc. So we have this equality condition. However, this equality condition is derived under the assumption a is the greatest number and c is the least number. So this one right here doesn't necessarily have to be c. This is just a place for the least number. For a general ordering, the equality condition can be stated as a equals b equals c, or one of a, b, and c is 0 and the other two are equal. Let's move on to problem B. As a special case, obtain an inequality with a to the fourth power plus b to the fourth power plus c to the fourth power plus abc times a plus b plus c on one side. So here's the inequality that we just proved, and the fourth power can appear if we let r equals 2. Letting r equals 2, the left-hand side of the inequality is a squared times a minus b times a minus c plus b squared times b minus a times b minus c plus c squared times c minus a times c minus b. Expanding the last two factors in each term gives this expression. Here, let's try to collect this a to the fourth power plus b to the fourth power plus c to the fourth power plus abc times a plus b plus c part, which is asked in the problem. The fourth power can appear by this times this, and this times this, and this times this. These three gives a to the power 4 plus b to the power 4 plus c to the power of 4. Next, let's deal with these plus terms. Multiplying with these parts give a squared bc plus ab squared c plus abc squared. And then we have the remaining minus terms, which can be written like this. So this part is equal to a to the fourth power plus b to the fourth power plus c to the fourth power plus abc times a plus b plus c. And if we expand the remaining parts, we obtain minus a cubed c minus a cubed b minus b cubed c minus ab cubed minus bc cubed minus ac cubed. And this must be greater than or equal to 0. Therefore, we obtain an inequality a to the fourth power plus b to the fourth power plus c to the fourth power plus abc times a plus b plus c is greater than or equal to a cubed c plus a cubed b plus b cubed c plus ab cubed plus bc cubed plus ac cubed. You can leave the right hand side like this, or you can rearrange it, and there are many ways to do so. If you focused on the fact that there are a cubed, b cubed, and c cubed terms and use them to group terms, for example, if you select a cubed c and a cubed b and group them with a cubed, you'll obtain a cubed times b plus c, and as for the entire right hand side, you'll obtain the inequality with the right hand side a cubed times b plus c plus b cubed times c plus a plus c cubed times a plus b. Or if you focus on the fact that there are two terms that contain same two letters, for example, a cubed b and ab cubed both contain only a and b, then you can group them by a common factor ab and obtain a squared plus b squared. This method gives the right hand side ab times a squared plus b squared plus bc times b squared plus c squared plus ca times c squared plus a squared. And this is perhaps the most helpful form to solve the next problem, considering the inequality we have to prove in that problem. So what is the next problem? The next problem is, show that if ABC equals 1 for positive numbers a, b, and c, then we have this inequality, a to the fourth power plus b to the fourth power plus c to the fourth power plus a cubed plus b cubed plus c cubed plus a plus b plus c is greater than or equal to a squared plus b squared divided by c plus b squared plus c squared divided by a plus c squared plus a squared divided by b plus 3. We start from the result of the previous problem, and let us actually use what I call the most helpful form, where the right hand side is ab times a squared plus b squared plus bc times b squared plus c squared plus ca times c squared plus a squared. We have the condition abc equals 1 and a, b, and c are positive. Then ab equals 1 over c, bc equals 1 over a, and ca equals 1 over b. Hence we have a to the fourth power plus b to the fourth power plus c to the fourth power plus, this is 1, so just a plus b plus c is greater than or equal to a squared plus b squared over c plus b squared plus c squared over a plus c squared plus a squared over b. This is sort of a middle result. Now, if you obtain the less helpful form from the previous problem, with cubes on the right hand side, and intended to use it anyway, then you'll need to take a smart detour. The goal here is to make square terms appear in the numerator while keeping only single variable to the denominator. So we have to split these cubic terms, like we split a cubed into a squared, then a inside the parenthesis, b cubed into b squared times b in the parenthesis, and c cubed into c squared times c in the parenthesis. So now we have a squared, b squared, and c squared, and if we apply abc equals 1, we have this, which rearranges to the same middle result that we just obtained. Comparing this middle result to the end result that we want to prove, you'll notice that we need cubic terms on the left-hand side and 3 on the right-hand side. This can be easily obtained. Given that a, b, and c are all positive, we can simply use the arithmetic mean geometric mean inequality for 3 variables to obtain that a cubed plus b cubed plus c cubed is greater than or equal to 3abc, and this is just 1, hence just 3. And if we add this to the middle result that we obtained the end result that we wanted to prove. By the way, there is another way to obtain the second inequality we need. I think many of you are already familiar with the factorization formula for a cubed plus b cubed plus c cubed minus 3abc. But I'm not going to use this formula. I'm going to use the slight modification on that formula, which is that this part can be also written as 1/2 times a minus b squared plus b minus c squared plus c minus a squared. This expression is non-negative when a, b, and c are positive. Therefore, we obtained a cubed plus b cubed plus c cubed is greater than or equal to 3abc, hence 3. So this concludes problem B3, and let's move on to problem B4. Problem B4. Here we have the equation 20 times x to the power of k plus 24 times y to the power of n is equal to 2024. Find all solutions of the following equation where it is required that x, k, y, and n are positive integers with the exponents k and n both greater than 1. There are occasionally more than one method to solve the equation, and this problem deserves to be solved by two methods. The first method is what is listed in the official solution. In this method, we first solve the simpler version of the given equation. 20 times a plus 24 times b equals 2024, where a and b are positive integers. Then, after we find possible values for a and b, we attempt to find the cases where a and b can be expressed as x to the power of k and y to the power of n respectively. The second method is how I initially solved this problem. When solving equations with integer solutions, you can often narrow down cases by considering the possible rightmost digits or ones digits of a variable. This is a really special case of modular arithmetic with mode 10. Let's start with the first method. Here, let us solve the simpler problem 20 times a plus 24 times b equals 2024, where a and b are positive integers. There is one easy to find solution, such as a, b equals 100, 1. This gives the left-hand side 2000 plus 24, hence 2024. But what about the other solutions, which I will call a prime, b prime? Well, since a, b, which is 100, 1, and a prime, b prime are both solutions to the above equation, we know that these two equations are true. If we subtract one equation from the other, we can eliminate the constant term 2024 and obtain 20 times a minus a prime plus 24 times b minus b prime equals 0. We can further divide both sides by 4 and rearrange to obtain 5 times a minus a prime is equal to negative 6 times b minus b prime. Here, 5 and 6 are co-prime, and a minus a prime and b minus b prime are both integers. Therefore, a minus a prime must be a multiple of 6. Hence, it can be written as a minus a prime equals 6k for integer k. Moreover, b minus b prime must be a multiple of 5, but due to this relation, they are dependent on each other. You can easily find out that b minus b prime is expressed as minus 5k. Therefore, a prime and b prime are related by parameter k, given by a prime equals a minus 6k and b prime equals b plus 5k. Therefore, if we know one solution a, b, such as 100, 1, then all the other solutions are of the form a minus 6k, b plus 5k and can be found by plugging in different values of integer k. The solution 100, 1 can be considered a case where k equals 0. Because b prime must be a positive integer, we must increase the value of k. And by increasing the value of k, we find these positive integer solutions. The process is simply keep subtracting 6 from previous value of a and adding 5 from previous value of b. So there are 17 positive integer solutions for the equation 20 times a plus 24 times b equals 2024. As for the next step, which is tackling the originally given problem, in which of these 17 cases can a and b be expressed as a equals x to the power of k and b equals y to the power of n? Well, if you investigate these 17 pairs, you'll notice that only these two pairs are of the form x to the power of k and y to the power of n, 100,1 and 4,81. Here, as for these four integers, 100 is 10 squared, and 1 is interesting since it can be expressed as 1 to the power of any integers n, and 4 equals 2 squared, and there are two possible expressions for 81, 3 to the power of 4 and 9 squared. Therefore, we have solutions x, k, y, n equals first 10, 2, 1, and n can be any integer greater than 1, 2, 2, 3, 4, and 2, 2, 9, 2. And let me show you the second method, which involves considering the possible rightmost digits of a variable, which can be expressed by modulo 10 arithmetic. In our given equation, the term that draws our immediate attention is this 20 times x to the power of k, since it is a multiple of 10. Therefore, we rearrange terms as 20 times x to the power of k equals 2024 minus 24 times y to the power of n. Dividing by 2, we obtain 10 times x to the power of k equals 1012 minus 12 times y to the power of n. And this right-hand side is multiple of 10, or you can say congruent to 0 mod 10. This means that 12 times y to the power of n is congruent to 2, or you can say the rightmost digit of 12 times y to the power of n is 2. And if you think about y to the power of n, you'll notice that y to the power of n must have rightmost digits of 1 or 6. This means that we need to divide into two cases, one where the rightmost digit of y to the power of n is 1, and the other where the rightmost digit of y to the power of n is 6. But before we do that, let us also determine the range of y to the power of n. From 10 times x to the power of k equals 1012 minus 12 times y to the power of n, this expression must be positive. This gives the range for y to the power of n, which must be less than 84 times 333, so on. So whenever we are thinking about possible values of y to the power of n, we must also consider this range condition as well. With this in mind, let us consider the first case where the rightmost digit of y to the power of n is 1. Now let's search for the possible rightmost digit of y. First, you can easily find out that y must be an odd number, because if you assume that y is even, then its natural number power cannot have the rightmost digit of 1 whatsoever. And with further investigation, you'll notice that the possible rightmost digits of y are 1, 3, 7, and 9. That is, y can have any odd number rightmost digits except 5. I mean, 1 is obvious, since any integer powers of 1 ends with 1, but you can also easily find examples where powers of 3, 7, and 9 end with 1. Also, let us consider the range condition. Due to the restriction that y to the power of n must be less than 84.33, 3 to the 4th power is a valid candidate for y to the power of n, but 7 to the power of 4 is an invalid candidate. So what are the cases that satisfy both conditions? Y ends with 1, 3, 7, or 9, and y to the power of n is less than 84.33. Well, there are these possible cases. Let me explain in more detail, and let's remember that we have the condition that n must be greater than 1. First, if y ends with 1, then y to the power of n must be of the form 1 to the power of any integer n. Any other cases, such as 11 squared, 111 squared, etc., all give values that are greater than 84.333. As for the case where y ends with 3, then there is only one possible case where y to the power of n equals 3 to the power of 4, hence 81. You see, the next smallest case with base 3 is 3 to the power of 8, which is obviously greater than 84.33. And if we try another base such as 13, the smallest possible value 13 to the 4th power is also greater than 84.33. As for the case where y ends with 7, then there are no possible cases, because the smallest power of 7 that ends with 1 is 7 to the power of 4, which is greater than 84.33. Similarly, if y ends with 9, then the only possible case is where y to the power of n equals 9 squared, hence 81. Therefore, we have these three possible cases for yn n. 1 to the power of any integer n, 3 to the power of 4, and 9 squared. Actually, we only need to divide into two cases, because 3 to the 4th power and 9 squared are the same, hence they have the same effect in the equation. So first, y equals 1, and n can have any integer values greater than 1. Then 10 times x to the power of k, which is equal to 1012 minus 12 times y to the power of n, gives the value 1012 minus 12, hence 1000. This means that x to the power of k equals 100, which can be expressed as 10 squared. The only possible integer solution where k is greater than 1 is when x, k is equal to 10, 2. Therefore, we obtain a solution x, k, y, n equals 10, 2, 1 and any integer n. Next, where y to the power of n is either 3 to the power of 4 or 9 squared. In this case, 10 times x to the power of k is equal to 40. So x to the power of k equals 4, hence 2 squared, which means that x, k equals 2, 2. And because we have two possible pairs for y, n, namely 3, 4 and 9, 2, we have two solutions for this case. X, k, y, n equals 2, 2, 3, 4 and 2, 2, 9, 2. But we are not done here. Remember that we have another possible rightmost digit for y to the power of n, which is 6. Well, we have to deal with this case as well. Similarly, we search for rightmost digits of y. This time, y must be even, and among even numbers, 2, 4, 6, and 8 are possible. That is, every even number digit except 0. And if we consider the range condition simultaneously, we obtain these possible values for y to the power of n. When the rightmost digit of y is 2, the only possible case for y to the power of n is 2 to the power of 4, and when y ends with 4, then the only possible case is 4 squared, and when y ends with 6, the only possible case is 6 squared, and when y ends with 8, then there are no possible cases. To summarize, y to the power of n can only have values 2 to the power of 4, 4 squared, and 6 squared. Any other numbers that end with digit 6 are greater than 84.333, hence violating our range condition. This time we also need only two cases, because 2 to the power of 4 and 4 squared are the same. So the first case, y to the power of n equals 2 to the power of 4, which also equals 4 squared. In this case, 10 times x to the power of k equals 820, hence x to the power of k equals 82. However, there are no possible integer solutions with k greater than 1 such that x to the power of k is equal to 82. As for the second case where y to the power of n equals 6 squared, now we have 10 times x to the power of k equals 580, hence x to the power of k equals 58. Again, there are no possible positive integer solution with k greater than 1 such that x to the power of k equals 58. Therefore, there are no solutions for case 2, hence the entire solutions are from case 1, which are 10, 2, 1, any n, 2, 2, 3, 4, and 2, 2, 9, 2. Problem B5. Problem A. Find all complex solutions of z to the 6th power equals z plus z bar, the complex conjugate of z. Problem B. For an integer n greater than 1, how many complex solutions does the equation z to the nth power equals z plus z bar have? So starting from problem A, first, you can easily notice that z equals 0 is a solution to the given equation. This is rather a trivial solution, so from now on, I will assume that z is non-zero and try to find some non-zero solutions. We have to use the polar form of complex numbers, so let's z as r times cosine theta plus I sine theta. Then the equation z to the 6th power equals z plus z bar becomes the left-hand side is r to the 6th power times cosine 6 theta plus I sine 6 theta, and the right-hand side is r cosine theta plus I sine theta plus its complex conjugate r times cosine theta minus I sine theta. So we have the equation r to the 6th power cosine 6 theta plus I sine 6 theta equals 2r cosine theta. Therefore, if we compare imaginary parts and real parts, from the imaginary part, we have r to the 6th power sine 6 theta equals 0, and because r is non-zero, we have sine 6 theta equals 0. And from the real part, we obtain the relation r to the 5th power cosine 6 theta equals 2 cosine theta. All we have to do is to obtain possible values of r and theta from these two relations. But let us do so in a smart way. You see, from sine 6 theta equals 0, we can obtain 12 possible candidates for theta in the typical range of the argument theta is greater than or equal to 0 and less than 2 pi. Examining the real part relation for these 12 cases will give us the solutions, but it will be tedious work. So let us think about the method that allows us to deal with multiple solutions at the same time, and also will be useful for more general next problem as well. The key here is to realize that we know the exact value of sine 6 theta. This allows us to find the exact values of cosine 6 theta, which is either 1 or negative 1. This allows to do multiple things. First, from the real part relation which contains cosine 6 theta, we can solve for cosine theta in these two cases. Notice that one case gives positive cosine theta and the other case gives negative cosine theta. That is, we can determine the sign of cosine theta. Moreover, this also means that cosine 6 theta plus I sine 6 theta is also equal to 1 or negative 1, because sine 6 theta is 0. This means that if we let z0 be the complex number cosine theta plus I sine theta, I used subscript 0 here because z is already used to denote the solution, which is just z0 part times absolute value r. Then, the above relation can be written as z0 to the 6th power is equal to either 1 or negative 1. This discovery will benefit us greatly because these are the equations that are much easier to solve compared to the original equation given in the problem. Using this result, instead of 12 cases, we only need to divide into following two cases. The first case is when cosine 6 theta equals 1, which leads to the result z0 to the 6th power equals 1 and cosine theta is positive. The second case is when cosine 6 theta equals negative 1, which leads to results z0 to the 6th power equals negative 1 and cosine theta is negative. Let us take a look at each case more carefully, starting from the first case. In this case, we have z0 to the 6th power equals 1, and like I said, this is a easier equation because now all roots are on a unit circle on the complex plane. More specifically, 6 roots of this equation are given like this. One root is always 1. other roots are on the vertices of a regular hexagon inscribed in a unit circle, with one of the vertices located at the obvious root 1. Mathematically speaking, the roots are z0 is equal to cosine theta plus I sine theta, with argument theta being 2k pi over 6, where k can have values of 0, 1, 2, 3, 4, and 5. However, we also have additional condition that cosine theta must be positive. If you have learned trigonometry, then you must have also learned that cosine theta is positive when the argument theta is on either first or fourth quadrants, or the argument theta is 0, so the root is located on the positive real axis. Therefore, we must select the roots that also satisfy this argument condition. This is the case where theta is equal to either 0, pi over 3, or 5 pi over 3, which is the case where k is equal to 0, 1, and 5. The absolute value r is given as the fifth root of 2 cosine theta, and using these theta values, we obtained r values fifth root of 2, 1, and 1. Therefore, from z equals r times cosine theta plus I sine theta, we obtain these three solutions: fifth root of 2, 1 plus square root of 3i over 2, and 1 minus square root of 3i over 2. In the second case where cosine 6 theta equals negative 1, now we have to find the values of z0 satisfying the equation z0 to the 6th power equals negative 1. This one is trickier than the previous one, but still pretty easy. First, you can easily notice that one root is where the argument theta is pi over 6. That is, one root is cosine pi over 6 plus I sine pi over 6. You can easily notice that if you raise this root to the 6th power, then the argument becomes pi, hence the 6th power of this root becomes negative 1. Then, the other roots can be found by drawing a regular hexagon inscribed in a unit circle, now having this cosine pi over 6 plus I sine pi over 6 as one of its vertices. That is, now the argument theta is given as pi over 6 plus 2k pi over 6. You can easily notice that z0 to the 6th power becomes negative 1 when theta can have these values. Moreover, now we have the condition that cosine theta must be negative. And cosine theta is negative only if theta is on either second or third quadrants, or theta equals pi so that the root is located on the negative real axis. This corresponds to theta values of 5 pi over 6 and 7 pi over 6, which corresponds to k values of 2 and 3. Now the absolute value r is given as the fifth root of minus 2 cosine theta, and the above two theta values both gives r values of 10th root of 3. This gives two z values, 10th root of 3 times negative 3 plus I over 2, and 10th root of 3 times negative square root of 3 minus I over 2. Therefore, combining with case 1 and the trivial solution z equals 0, we have 6 solutions: 0, fifth root of 2, 1 plus minus square root of 3i over 2, and 10th root of 3 times negative square root of 3 plus minus I over 2. And now for more general case in problem B. For an integer n greater than 1, how many complex solutions does z to the nth power equals z plus z bar have? We have already developed all the methods we need in the previous problem, so here we will just follow the same process, now with the general version of the equation. First, we have a trivial solution z equals 0. From now on, it is assumed that z is non-zero. Let's use the polar form again and let z as r times cosine theta plus I sine theta. Then the equation now becomes r to the nth power times cosine n theta plus I sine n theta is equal to 2r cosine theta. And we do the same comparison with real and imaginary parts. Comparing the real part gives the relation r to the power of n minus 1 times cosine n theta equals 2 cosine theta. And comparing the imaginary part gives the relation sine n theta equals 0. And we do the same thing as in the previous problem. Sine n theta equals 0 gives cosine n theta equals plus minus 1. And these two gives cosine n theta plus I sine n theta equals plus minus 1. Therefore, writing cosine theta plus I sine theta as z0, we have the relation z0 to the nth power equals plus minus 1. Also, this allows us to determine the sign of cosine theta. Therefore, now we have these two cases. Case 1 is when cosine n theta equals 1, which gives z0 to the nth power equals 1 and cosine theta is positive. Case 2 is when cosine n theta equals negative 1, which gives z0 to the nth power equals negative 1 and cosine theta is negative. So the first case, z0 to the nth power equals 1 and cosine theta is positive. In this problem, we don't need to find the exact solutions. We only need to find the number of solutions. In the previous problem, we searched for possible values of z0. Each z0 has its own unique argument theta, which in turn determines the value of absolute value r, hence uniquely determines the value of z, the root of the original equation. With this knowledge, we only need to count the number of valid values for z0, and we only need to care about the sign of cosine theta. Cosine theta being positive means that only roots on first or fourth quadrants or with zero argument are valid. So the question is this: how many roots of the equation z0 to the nth power equals 1 are on such locations? Well, some of you might not like this method, but sometimes it does help if we just go brute force mode and sketch the roots for several values of n. It will help us find some patterns. The roots form n vertices of regular polygons, that is, vertices of regular n-gons. One of these n roots is always 1, located at here, and using this property will help you draw correct polygons. The numbers on the top right show how many roots satisfy cosine theta is positive condition. So, can you find any rules or patterns as to how these numbers change? Well, if we want a general result, we have to divide cases. When n equals 4k, we have 2k minus 1 valid roots. When n equals 4k plus 1, 4k plus 2, or 4k plus 3, then we have 2k plus 1 valid roots. Let's take a look at n equals 4k case first. This is the case where both I and minus I are roots of the equation of z0. However, because these two roots are on the imaginary axis, both are invalid roots. This leaves 4k minus 2 remaining roots, and because of the symmetry in this case, only half of them, hence 2k minus 1 roots, have positive real parts and thus satisfy the cosine condition. As for n equals 4k plus 1, 4k plus 2, or 4k plus 3 cases, we know that 1 is always a valid root, even in n equals 4k case. In all cases, the argument increases by 2 pi over n as we move on to the next vertex of a polygon. When n has values of 4k plus 1, 4k plus 2, or 4k plus 3, if we multiply this amount by k, then it is less than pi over 2, and if we multiply this amount by k plus 1, then it becomes greater than pi over 2. This means that there are k roots, each on first and fourth quadrants, in each of this right angle. Hence the number of valid roots are 1 plus k, hence 2k plus 1. So these are the results for case 1. But we also have case 2, where cosine n theta equals -1, hence z0 to the nth power equals -1, and cosine theta is negative. Cosine theta being negative means that only roots on second or third quadrants, or with argument pi, are valid roots. So let us sketch the roots of the equation z0 to the nth power equals -1 and investigate how many of them satisfy such conditions. Because now the right-hand side of the equation is -1, the polygons are arranged in a slightly different manner. One observation you can use this time is that one root of the equation is always cosine pi over n plus I sine pi over n. This root is located right here. So now you can draw regular polygons knowing that this value must be one of the vertices. Another useful property is when n is an odd number, then -1 is also one of the roots, in addition to cosine pi over n plus I sine pi over n. That is this value right here. So we can draw the figures with the help of this knowledge, and we have these numbers, which are the numbers of the roots satisfying the cosine condition. So what would be the pattern for this case? Well, in this case, the behavior when n is an odd number, that is, either 4k plus 1 or 4k plus 3, can be described in a single category, but when n is an even number, we need to treat n equals 4k and n equals 4k plus 2 cases separately. Let me start with the odd number case. Contrary to case 1, now we have a valid root -1. But this is just a mirror image of case 1. So we have case 1 figure right here, but if you just flip the entire figure over the imaginary axis, then you will obtain the figure for case 2. Also, the cosine condition for the valid roots are also symmetric if you compare case 1 and case 2. The real part must be positive in case 1, and the real part must be negative in case 2. Therefore, the same logic as in case 1 also applies here when counting the number of valid roots. So just like case 1, we have 2k plus 1 valid roots. Moving on to even numbers, n equals 4k case is really simple. Half of the roots are on the left and the other half are on the right. So 2k roots on the left and 2k roots on the right. Therefore, there are 2k valid roots. As for n equals 4k plus 2, now this is the case where we have I and minus I as roots. Both are invalid roots because they are on the imaginary axis. So we have 4k roots remaining, and they are arranged in a manner that half is on the left and half is on the right, so 2k on the left and 2k on the right. Therefore, even the layout of vertices is a bit different. We also have 2k valid roots. So we finished case 2. Now we can combine cases 1 and 2 and find the total number of roots of the original equation. So we have case divisions for n here. N equals 4k, 4k plus 1, 4k plus 2, or 4k plus 3. And note that we must also count the trivial root z equals 0 as well. For case 1, we found that the number of roots are 2k minus 1, 2k plus 1, 2k plus 1, and 2k plus 1. And for case 2, we found that the number of roots are 2k, 2k plus 1, 2k, and 2k plus 1. If we add up everything on the same row, we obtain the total number of roots for each case division for n. And if you examine the total number of roots, you'll notice that the number of roots are n roots when n is equal to 4k, 4k plus 2, or 4k plus 3, and n plus 2 roots when n equals 4k plus 1. The last problem, problem 6, is ridiculously long that it barely fits in a single page. But you don't have to read all of this right now. I will explain each problem in bigger texts whenever it is time to do so. Before we get to the actual problems, first we have this part, which explains some rule or algorithm. So let's see what it says. a list of k elements, possibly with repeats, is given. The goal is to find if there is a majority element. The majority element is defined to be an element x such that the number of times x occurs in the list is strictly greater than k over 2, half the length of a list. There need not be such an element, but if it is there, it must be unique. A celebrated efficient way to do this uses two functions f and m with domain 1 to 3 ... k. The functions are defined inductively as follows. First, define f of 1 as the first element of the list and m of 1 as 1. Then, assuming f and m are defined for all inputs from 1 to I, define their next values. F of I plus 1 is defined as f of I if m of I is positive, and it is defined as the I plus 1th element of the list if m of I is 0. As for function m of I plus 1 is defined as m of I minus 1 if m of I is positive and I plus 1th element of the list is other than f of I, and m of I plus 1 in other cases. These rules seem a bit complicated to understand at first glance, and that's why we have this problem A. For the example of length 15 given below, so we have this list of 15 letters, write a sequence of 15 letters showing the values of f of I, and a sequence of 15 numbers directly underneath showing the values of m of I for all I values. So we have the rules right here, and let's fill up this table. We start with the first element a and number 1. The rule for function f is that whenever the value of function m is non-zero, the next value of function f is the same as the previous one and changes to a new element only if function m is 0. As for function m, we need to be aware of when this function can decrease, and that is when the current element of function f is different from the next element of the list, provided that the function is not already 0. If that's not the case, then we simply increase the value. So if we move on to I equals 2, the value of function m is non-zero, so the element in function f does not change. It is still a. Moreover, the second element of the list is a, which is the same as the first value of function f. This fits into otherwise case, so the value of function m increases. Next, we still have positive value for m, so function f is still a, but now the next element of the list is b, which is different from a. Therefore, now the function m decreases. And we can go on and on. M is positive, so f is still a, and these are the same, so m increases. So m is positive, so f does not change, but now we have different elements, so m decreases. Again, m is positive, so f is still a, but c is different from a, so value of m decreases. The next is interesting case, because now we have function m having value of 0, which is this second case, by the way. And it is this case where the value of function f can change. So it changes into a new element of the list, which is c. Moreover, function m has to increase because when the value of m is 0, it fits the second case. So m is positive, so function f does not change, but b is different from c, so the function m decreases. So the function m becomes 0 again, which means that function f can change into a new element, now b. And when the value of m is 0, function m increases. So m is positive, so f does not change, and we have same elements, so function m increases. M is positive, so f does not change, and a and b are different, so function m decreases. M is positive, so function f does not change, and we have same elements, so function m increases. Again, m is positive, so f stays at b, and we have the same element b in the list, so function m increases. M is positive, so f is still b, but c is different from b, so function m decreases. And finally, m is positive, so function f gives b, and we have b here and b here, so function m increases to 3. So we have filled the table. The majority element of this list is b. It occurs 8 times on the list of a length 15. Now, what does this have to do with functions f and m? We'll explore that in the following questions. Problem B. Prove that in general, the list can be divided into 2 disjoint parts A and B, such that part A contains m of k elements of the list, each of which is f of k. And part B contains the remaining k minus m of k elements of the list, and B can be written as disjoint union of pairs such that the 2 elements in each pair are distinct. This is really difficult to understand just by reading the statements, so let us bring back the list from the previous problem. In this example, the length of the list k is 15. In investigating the final values of f and m, we know that f of k is b and m of k is 3. Here, I will divide this list as follows. I divided the list into 2 parts, A and B, just as claimed in the problem. If we take a look at part A first, it consists of 3 elements, which is the value of m of k, and those 3 elements are all B, which is the value of f of k. So part B consists of remaining 12 elements, and we can group these elements by 2, for example, like this. Then we can write part B as a list of pairs of elements, in this case 6 pairs. And I only grouped 2 different elements into a pair, so 2 elements in each pair are always distinct. And we have to prove that this kind of division is possible for any list. We are going to use mathematical induction. First, we need to check the base case, which is when the list has only 1 element, hence f of I is just that element and m of I equals 1. Here, we can consider part A as this 1 element and part B is empty. Then the conditions for parts A and B are true in this case. Next, we need an induction hypothesis, which is that the list having length of I can be divided into 2 parts A and B, satisfying the conditions given in the problem. Then we consider introducing I plus 1th element to the list, and we have to think about this. How should parts A and B change so that the parts in the new list still satisfy the conditions given in the problem? We need case division, and let's think about the first case, that is when m of I equals 0. One example of this case is a list of 6 elements taken from our previous 15 element example, and we want to introduce a new element c to this list. In this case, the current value of function m is 0. And because m of I is 0, function f must change its value to a new element c, and because m of I is 0, it can only increase, hence the next value of m is 1. It is stated in the problem that m of I is also equal to the number of elements of part A. Therefore, m of I being 0 means that currently part A is empty, and all I elements belong to part B, which is possible in this example, by the way, since we can pair up the elements as shown here. In this case, we let the newly introduced I plus 1th element as a new part A, while part B remains unchanged. Then we have the list with length I plus 1 divided into 2 parts that satisfy the given conditions in the problem. Notice that now part A contains 1 element, which is indeed equal to the value of m of I plus 1. Let's move on to case 2. which is now m of I is positive and the I plus 1th element of the list is the same one as f of I. From our very first 15 element example, having 3 elements already and attempting to introduce 4th element a belongs to this case, as the value of m of I is 1, hence non-zero, and the new element a is the same as the previous element of function f. Here, the previous list can be divided into part A and part B satisfying given conditions, like this for example. In this case, part A has 1 element, which is the value of m of I. In this case, we put our new I plus 1th element to part A, and part B remains unchanged. Notice that in this case, both the size of part A and the value of function m increase by 1. Here, function m increases because the same element as f of I is being introduced. Therefore, new parts A and B still satisfy the given conditions. Let's take a look at the third case, which is m of I is positive, but I plus 1th element of the list is different from f of I. Actually, the good example of this is just take the example of 4 elements from case 2 and try to introduce the 5th element, but this 5th element is b, which is not the element stored in function f. In this case, first we remove one element from part A, which exists as long as the value of function m is non-zero. Then we pair this removed element with the newly introduced I plus 1th element and add this pair to part B. This newly formed pair consists of 2 distinct elements, because in this case the newly introduced element is different from f of I, which is the element that belongs to part A. Also, in this case, both the size of part A and the value of m decrease by 1, hence new parts A and B still satisfy the given conditions. So we have examined all possible cases, and this concludes the mathematical induction proof. Moving on to problem C, if there is a majority element, show that it must be f of k. We are going to use the result of problem B. In the previous problem, we proved that the list can be divided into parts A and B, and elements in part B can be grouped into pairs where 2 elements from any pair are distinct. This leads to the following important property of part B. Because all pairs in part B consist of distinct elements, the most occurring element of part B cannot occur more than half the size of B times in part B. If it occurs more, then by the pigeonhole principle, there must exist a pair where 2 identical elements belong to that pair. But the majority element, as defined in the problem, must occur more than k over 2 times in the list. This means that if there is a majority element, then it must be in part A. But all elements in part A are f of k, hence the majority element must be f of k. And this concludes the proof. Next, problem D. Assuming f of k is the majority element, answer the following 2 questions. First, show by examples that the number of occurrences of f of k in the list does not determine the value of m of k. Can the value of m of k be anything from 0 to k? Find the constraints, if any, on the possible values of m of k. Alright, so part 1, showing that the number of occurrences of the majority element f of k does not determine the value of m of k. There's nothing much to explain here. If you have a pretty solid understanding of how values of function f and m change, then you'll be able to quickly come up with counterexamples. I will show you these 2 lists, ABCCC and AACCC. Both lists have length 5, both have the majority element C, and the number of occurrences of the majority element is also the same for both lists, 3 times. However, the value of m of 5 differs, where the first list gives m of 5 equals 3, and the second list gives m of 5 equals 1. In the next part of the problem, finding some constraints on the values of m of k. There are actually several constraints for m of k, and I will explain them one by one. First, from the previous problem C, we have shown that if the majority element exists, it must be in part A. And it is also established in problem B that part A contains exactly m of k elements. Therefore, if the majority element exists, then m of k, which is equal to the size of part A, must be non-zero. Second, also from problem B, it is explained that part A consists only f of k as its elements, and m of k is equal to the size of part A. This means that the element f of k occurs in the list at least m of k times. However, the element f of k may also exist in part B. Therefore, we know that m of k is less than or equal to the number of occurrences of f of k. Lastly, the function m of k starts from 1 when k equals 1 and changes by 1, that is, either increases or decreases by 1, as the length of the list k increases by 1. This means that m of k has the same parity as k. Note that constraints 2 and 3 are true regardless of whether there is a majority element or not. As for final problem E, now assume instead that an element occurs exactly k over 2 times in the list. Is it necessary that f of k is such an element? Well, the answer is no. And I can give you this counterexample. The list is ABCA, so the length of the list is 4. Here, element A occurs exactly twice in the list. However, element f of 4 is C instead of A. So we have dealt with problem E as well. And with this, we are done with problem B6. Hence, we are done with every problem in part B of the Chennai Mathematical Institute's Bachelor of Science Entrance Exam 2024. Thank you all for watching. Please hit the like button if you enjoyed this video, and I will see you in another video.